And we're back. Welcome back from the weekend and happy Tuesday. Today we'll be continuing on in our conversation about components of the end-to-end pattern recognition system, the pipeline as it were. But before we do that, we'll begin with a few administrative bits. The reading. Please make sure you're getting through both the prologue and chapter 1 in the FLAC machine learning text. That's pages 1 through 48. And of course, homework 1 is due on the 2nd of September. That's Wednesday night, 1 second before midnight at 11:59 and 59 seconds p.m. There will also be a 15-minute presentation from each of you in the class meeting on Thursday, the 3rd of September, so this Thursday at 4:30. So you'll be handing in your presentation the night before, the presentation that you will be presenting the next day, and you'll be each doing a 15-minute presentation as our class meeting period on Thursday, the 3rd of September. Okay, so we've been talking about the end-to-end pattern recognition system, and last time we talked about the sensor component, and the sensor is that apparatus, could be software, could be physical device, that provides you the basic information that arrives, the so-called patterns that describe some object or phenomenon in the environment. And so we talked about the mammalian visual system, and we mentioned this because this is where computer vision or cameras come from. And we segued into an engineering abstraction of the mammalian visual system, ending in our digital image from our CCD or CMOS array. We made a geometric abstraction, and we coined the term focal plane, where the rays of light come to a focal point, a single point. And we talked about the image plane, and the distance between that image plane and the focal length had an impact on the amount of light you collected, and as well as the size of the image that was returned by this digitization process in the engineering abstraction. We also went into the representation of an image in the so-called color space. We examined that in MATLAB, looking at the various slices and converting this to grayscale. So we got an image, this following image. I called it Is a Dog's Life, dog on a boat enjoying himself, just relaxing. Now from that image, the focus of today is to take that raw sensor information and to perform feature generation. And that's going to be the subject for today, and we'll carry forward that image example and talk about feature generation specifically for images. And so feature generation, as we said in the first module for this semester, describes the processes and decisions about the form of representation that you assume for each object within the data obtained from the sensors. And so this could be by extracting some raw information returned by the sensors. It could be an arbitrary statistic. So that's going to be our focus for today. So let's take a look at the first part of our representation, something called intensity surface. So we're going to make the assumption that you have a grayscale image, but this is absolutely possible with color imagery. You can just imagine a grayscale image has values from 0 to 255 at each pixel in each location. But if you're talking about color, you have 3 such images, one for the red channel, one for the blue channel, one for the green channel for an RGB representation. So every operation that we're going to talk about for grayscale would be performed in color imagery or on color imagery on a single color plane or color channel from our RGB representation. So we have our grayscale image, and you can imagine you lay it down on the ground or on planar surface like a carpet. Just lay it all out. Now, when you lay it out, of course, we're going to need some way, and we'll impose some axes on it, that we're going to use to measure the position of a pixel within that image. We need to be able to identify where they are. So in this coordinate system, we're going to have a horizontal component, we'll just call that X, and a vertical component, we'll call that Y. And each XY defines the unique position of a pixel within that image as defined by the coordinate frame that we've represented with the red axes. And so in the upper left-hand corner of our image that we've laid out on horizontal surface like carpet, we have the origin of this coordinate system. And these are so-called image coordinates that allow you to identify within the image the position or location of some pixel. So we imagine the value then of this image at a particular location. In this case, it's grayscale. And so 0 would represent black, and 255 would represent white, maximum intensity. And so the image, we think of it as a two-dimensional function, and it takes on gray values or assigns gray values or associates gray values with every single tuple xy describing a position in image coordinates. And so this intensity image function is often called an intensity function. And we call that or note that with I. I is of arity 2, so it takes a tuple, double, consisting of the x and y coordinates in image coordinate system. And so this image returns a value for each pixel location, this intensity function as it's called, in the closed interval on the integer number line, positive integer, between 0 and 255. Okay, so we think of black as the least intense value of a pixel, and we think of white as being the most intense, where I is that so-called intensity function that gives you these various pixel values for each tuple you give it, describing coordinate in image coordinates, i.e. a location on this image. Okay, so we think of this intensity or this so-called gray value because, as we said at the outset, this is a gray scale image, or you're talking about the intensity of the red channel, the green channel, the blue channel, if you're dealing with the individual color channels in an RGB representation. This third axis we're going to call the intensity axis. And this intensity axis is going to represent intensities anywhere from 0 through 255. And we measure intensities as integers, as positive integers. Okay, so you can think of the gray level value or the pixel intensity value at a particular location in image coordinates x1, y1 in this case, as we've marked it. You can think of it as the height or the size of the intensity. So at pixel location x1, y1, let's assume that the intensity function returned a value of 100. So that means we have, for image coordinate x1, y1, we have some particular intensity. In this particular case, we're just assigning this 100. And so if we do that and we project this intensity of 100 back to the intensity axis, of course, we mark off 100 here. And the height of this particular pixel location, this intensity, is represented as a height here. And so here we draw this black line segment, and the height of it is 100 because the intensity surface value, the intensity at that location in the image coordinates x1, y1 is 100. So we treat this third axis, the z-axis, if we want to call it that, as our intensity axis. Okay, so let's go to another location, and let's say at this other next location, at location x2, y2 in image coordinates, we have intensity value of 160. And so we'd mark 160 on the intensity axis, and we can project this line segment from location x2, y2 in image coordinates up, and you'll notice this second location, x2, y2, the intensity, if we look at that height of that line segment, the intensity is taller than the intensity at the first location, x1, y1 in image coordinates. And so we draw this other intensity point, and we can do this again, maybe at location x3, y3, a third one. So this intensity function, I, returns a 160. Let's imagine that at this third location, x3, y3, in image coordinates. And we notice that, of course, if we represent the height of the intensity surface at location x3, y3 in image coordinates, it's the same as the height in location x2, y2. And so some pixels will have the same intensity. Some pixels will have greater intensity. Some will have less intensity. And so there are certain properties such as so-called color constancy. And this can help us. And what color constancy says is that nearby pixels corresponding to close by areas in the material for a particular object typically have intensities that are close in value, right? And so some color constancy tells us a little bit about objects that are depicted in an image, right? Because objects more likely, pixels close by, if it's the same object, tend to be the same color or similar. Things that are further away, the color changes, but it doesn't change as dramatically over very short spans of image region. Okay, so let's then draw in this intensity of this last point in image coordinates at point x4, y4 in image coordinates. And let's say that returned the intensity function, returned intensity of 100. And you'll notice that the intensity at x4, y4 is less than the intensity at x3, y3. It's also less than the intensity at x2, y2, but it is the same as the intensity in image coordinates at location x1, y1. Okay, so this is the so-called intensity surface representation, because if you look at this, right, all of the intensities for every pixel in every location xy in the image, if you were to plot the intensities using these line segments, it would form a surface, a contour in 3 space, in R3 in this particular case. And so we take these intensity points, and because it forms a surface, if we wanted to characterize or describe the content of the image, we need to look at the shape of the intensity surface. So let's consider how we're going to do this. All right, so we have these intensities, and they form a surface. If we were to connect all of these intensity points for these intensities at each one of these image regions, points in the image coordinate system, the intensities are going to form a surface, and this surface has a shape to it. You might have flat planar regions, more smooth. You might have bumpy regions, or you might have inclines, be they inclines sloping up or inclines sloping downward. If we were to look at this particular example, and let me get my pen here, I'm going to select, let's select blue. Blue seems to work really well for us. If we were to look at the shape of the intensity surface going from x1, y1 to x2, y2, well, that corresponds to an incline that slopes upward, going from x2, y2 to x3, y3. Well, that's a flat plane, okay? And going from x3, y3 to x4, y4, well, that's a hill, an incline, sloping downward. You'll also notice that the incline sloping downward is much more dramatic than the incline sloping upwards. Okay, so in order then to describe this intensity surface and thusly describe the content of the image, it's important to describe the surface or the shape of the surface of the intensity surface to describe the flat planes, the bumpiness, or the inclines. Okay, so how do we do this? Well, we represent image features using statistics over the intensity surface. And the particular statistic we're going to look at is the change in intensity surface, in this case, the change in the z-axis, delta intensity, with respect to the change in the pixel value. So as we move or go across the image in the image coordinate systems, dx and dy, we're going to look at the dz axis, or the intensity axis, how that changes. So we're looking at the change in intensity surface as you move from one pixel location to the next in image coordinates. And that's what we're going to do. That's the statistic that we'll employ in order to measure the shape of the intensity surface. Okay, so how do we do this? Well, we can use spatial derivatives. We can take the partial derivative of this intensity surface, this intensity function with respect to x, and that would correspond to if you were to move your eyes and cast your sight from left to right in a so-called scan line. Let me set this pen color to red, or not red. Red's probably a poor choice. Let me set my pen color to cyan. Okay. So then if you imagine then a scan line, you go across the image along x in some direction, and you're looking at now the partial derivative with respect to x as you go from one location x to the next location x. That's your delta pixel, right? Your dx. You're looking at the change in the intensity surface, namely your change, your delta in your intensity function, right? So essentially what you're computing when you're trying to, and you can do this in the x direction of the image coordinate system or the y direction or diagonally in some angle. And so when you do this, you're measuring the steepness of the gradient, right? The magnitude of the gradient in some direction of the intensity surface. And this is how you characterize the shape of the intensity surface and thusly the content of the image. Okay, so you can also do this in the y direction. In that case, your scan line along which you're measuring intensity, change in intensity, is with respect to the y-axis, the y coordinate in image coordinates, the y-axis in image coordinates. All right, so let's take a look at this. So if we go across in the x direction in image coordinates, and we look at the scan line in image coordinates, what is that scan line telling us? Well, let's take a look at this vertical edge in the image, right, for that wall. We look at the scan line going in the x direction. We go from dark pixel, and in a very short space along x, we go to a very light pixel, and then we go from light pixel to very dark pixel. So we have a dramatic change in intensity value with respect to x. And so an edge, what we'll define as an edge point, is a large slope in some direction, like along the x direction. And so anytime we see a very large derivative in the intensity surface along a scan line, that's going to be a point that contributes to an edge. And so a vertical edge is nothing more than a large gradient or large slope in the x direction in image coordinates, a large slope in the intensity surface or the intensity function. Likewise, what is a horizontal edge? Well, if we look at our scan line in the y direction in image coordinates, here we go from dark pixel to light pixel back to dark pixel. A horizontal edge is comprised of a set of edge points, which are pixels, where along the y direction, we have a very large slope in the image intensity function. So a horizontal edge is nothing more, a horizontal edge in the image is nothing more than a large slope in the intensity surface function, the intensity function. So what does large mean, you might ask? Well, think about the top 5% steepest slopes in the intensity surface as you go along a scan line. And that's kind of like hypothesis testing. You're looking for these notional outliers. The biggest slopes are the crisp edges that describe the content of your image. Okay, so we have these edges in the vertical and horizontal direction, and we can identify or compute these edges using a horizontal scan line along the y direction or scan line along the x direction in image coordinate system. So let's say we have a vertical edge associated with a large slope in the x direction of the image coordinate in the image coordinate system. And so what does this mean? Well, let's look at what derivative means. So ddx, the derivative of some function, going back to the definition of a derivative, is f of x plus delta x minus f of x. Well, that's the change in the rise over delta x, that's the change in the run. So we're going in pixels, one pixel at a time, and we're looking at the difference in the intensity surface as you go from one location to the next, some delta x. All right, so let's replace this, our function, let's replace that with the intensity function. We have I, the intensity function, and I takes two parameters, x and y, and so we're going to change our ddx to the partial derivative because we're interested in how this intensity surface changes with respect to a single scan line direction in image coordinates, in this case, the x direction. So what's our f of x plus delta x? Okay, well, if we're scanning in the x direction, we're not changing the y coordinate. So here we have I of some value, comma y, I of some value, comma y. So now let's look at our image. So we have our next location, I of x plus 1, and we're going to subtract from that the previous location, right? So what we're going to do then, when we go across the image in pixels, we're going to go some number of hops away in this image, right? So we're going to look at it 2 pixels away, because delta x, we have the first pixel that we're in, and then we have the second pixel that we're in. And so here, this image, when we look at the first location where we're measuring the pixel intensity, it's I of x plus 1 comma y, because we're going to the right. And then we also have I of x minus 1. Now you might wonder, why am I not doing I of x? Because we want the slope at coordinate number x, right? So if we want the slope at x, we're going to have to do something a little bit differently. And let me illustrate that. So let me bring up the black pen, and let's say we have some function, and there's my function. And let's say we have, here's my f of x, and we have a point here, x, and f of x is right here. That's my f of x. Our function f evaluated at x. Okay, so this is my f of x. Now, if I want the slope of the line at f of x, so this is x. This is, if we were to go to the left of x, to the right of x rather, in pixels, this is x plus 1. If we will go 1 to the right for x, this is x minus 1. And so let's change the pen color. I'm going to change it to red, and I'm going to draw in what the slope of the function at x will be. And so if we take a tangent line, we draw a tangent line at f of x, the slope of that tangent line is going to be the slope of f at that point x, the slope of that tangent line. So this line comes into contact with the function f at that one point, f of x, and the slope of this tangent line is precisely the slope of this function at that point x. So if we have this tangent line and we want to know what the slope of that tangent line is, what do we need to do? Well, we measure the rise. This is the rise of that function. And we say rise over run is the slope. That's the run. So we have this triangle, and the slope of that tangent, treating the tangent line as the hypotenuse of a right triangle, the slope is just the rise over the run. Okay, well, what is the run? That's x plus 1 on one side, x minus 1 on the other side. That's how we get the slope. So here, if we look at how many pixels dx we're going to go, well, if we want the slope at that pixel, we need to go 1 pixel to the left. That's x minus 1. That's our x minus 1 in image coordinates. Here's my x in image coordinates, and 1 pixel to the right, that's x plus 1. So if we draw our tangent line and we want that slope, well, the dx, you go from x minus 1 to x, that's 1 pixel over. If you go from x to x plus 1, that's 2 pixels. So we get that denominator, delta x, is equal to 2. So when we evaluate the function, we evaluate the function to find the rise. Well, the rise is just the value of the function at the point to the right. So that's f of x plus 1, right? Minus the value of the function at that point. That's f of x minus 1. Okay? So that's exactly what I substituted here. This is the intensity at the point on the right of x in the image coordinates. This is the intensity for the point on the left of that point x in image coordinates, and this is the run. So we have the difference in the intensity function, the rise, the right minus left, and intensity function over 2. And that's exactly the implementation, going back to the definition of what the derivative is and what it means. Okay, so now that we've demonstrated this, okay, well, we're going to rearrange these terms. Everything here in this function is under a common denominator. And let's get the pen here. Let's do it in black, and I'll demonstrate precisely what I mean. So here we have 3 terms. We have a negative term here. We have minus I of x minus 1 comma y over 2. So minus 1/2 of I x minus 1 comma y. Okay, that's this term. We have 0 plus 0 plus this term, 1/2 of I times x plus 1 comma y. So if we take this function and decompose each of the terms, well, we have our minus 1/2 intensity function at the point on the left of x for the scan line in x direction. That's this term, right? So let's label this first term, second term, third term. So here we have the first term exactly as written. We have the second term here exactly as written. And now we have the third term here. That's the 1/2 times the intensity function on the scan line on the right-hand side of x in image coordinates. That's our third term here, 1/2 I of x plus 1 comma y. Now here, our second term, that's 0. How do we get 0? We multiply 0 times anything. So let's just say, let's multiply 0 times intensity function at position xy, right, on the scan line, that point between the left-hand point and the right-hand point from the previous slide. And so if we do that, now what we can do is we can represent this decomposed function describing our discrete derivative in terms of a bunch of weights. So let's take a look. Here we have a leading minus 1/2, we have a 0, and we have a positive 1/2. Well, here's minus 1/2, here's 0, here's positive 1/2. So we're going to build a special array, and this array is going to have 3 scalars in this case. Each scalar represents each one of these coefficients. Coefficient for the first term, minus 1/2, coefficient for the second term, 0, coefficient for the third term, which is positive 1/2. Okay, so this is a so-called convolution mask. And the purpose of this mask is going to be used to compute this derivative. It also has a name. It's called the central difference. And what it measures is the difference in the intensity function as you go from the pixel on the left of a center point and the pixel on the right of the center point for the scan line going in the x direction in image coordinates. And so here we have our coefficients. But if we look at what it means when we say I of x minus 1 comma y, well, if we center this mask over coordinate x comma y in the image, well, what is the coordinate of this mask to the left of it? If we were to place this mask over a pixel in xy in the center pixel. So if this center mask value was over a pixel in coordinate xy in image coordinates, then immediately to the left, that would be x minus 1 comma y as the image coordinate, x minus 1 comma y. So really, the value that is beneath this particular cell in my 3 array is going to be the value of the intensity function at coordinate x minus 1 comma y if I place this mask, a center position, over image coordinate at position xy. So what is the coordinate for this position to the right? That's x plus 1 comma y. So if I take this mask and I pick it up, let me get my pen here. if I take this mask and I pick it up and I put it over the image such that the center is at position xy, well, all I do is I take minus 1/2, multiply it by the intensity surface in the first position, add it to 0 times the intensity surface of the center position, add it to 1/2 times the intensity surface for the right-hand position in that 3 array. And if I sum those terms together, that's going to give me the so-called central difference, or the derivative, or the slope of the intensity surface at that center point, xy. And so I do this centering the mask at each position xy in the image. So at this position, at this position, at this position, and I slide that mask over 1 pixel at a time. Now, computationally, if you get to the point where the center position of the mask, say, is here, and the right-hand side is off and the left-hand side is on, well, you just pad a value and compute that as your slope. You could just make it the slope as the remainder, or you could just make it 0, constant, or just take the same value you had for the slope in the previous location, propagate that to the next location. There are all sorts of standard ways of filling in those edges when your mask falls off the edge, so to speak. So this is the so-called central difference operator. And the process of taking your mask, superimposing it over a region of the image, computing that central difference or derivative, and then sliding it 1 pixel to the right, is called convolution. And hence, this is called a convolution mask. And actually, MATLAB has standard operators in the computer vision toolbox for doing convolution in 1 dimension or in 2 dimensions on an image. Okay, so this results, this convolution mask, in a slope, the slope of the intensity surface centered at each image coordinate. And this slope computation is just the interpretation of our derivative, the definition, implemented as a discrete derivative. And it involves a statistic, the statistic we've just listed here, the central difference, using a sum or involving a sum. And so in this case, you sample every 3 pixels in the image. And in doing so, you can isolate the steepest edges or the steepest slopes in your intensity surface across the whole image. Now, for this image, if you were to do that, you would get the edges associated with this, looks like a fireplace or a turret or tower or something like that. Okay, so you can then isolate the steepest ones computationally by saying, okay, take the top 5% steepest slopes from this convolution operator resulting from doing the convolution over the entire image. Okay, so let's now take this basic measurement of the shape of the intensity surface, and let's finish out our conversation and talking about edges. Okay, so we have these slopes, or what I would like to call them now, edge points, and these are the individual slopes for each pixel relative to the scan line going in the x direction in image coordinates or in the y direction in image coordinates. Okay, so what is a line? Because when we look at the edge for this structure, we don't just think of slopes at points in the image, we think of entire lines. And so here, if we look along the top edge of this structure in the image, well, we have edges here. Those are horizontal edges. We have vertical edges like those. If we look at the bricks, they're horizontal edges, and they also have vertical edges. And so when we define the shape, we're not just interested in the individual slope at various locations in the image. We're concerned about a collection of slopes that are collinear, i.e. they form an edge or a line. So what exactly is this edge or line? A line is a one-dimensional figure that has no thickness and is determined by 2 points that passes through 2 points, so we'll call those points A and B. So line is uniquely determined by 2 points, and it passes through them, and we call these points A and B. Now, these points, in our case, just happen to be these slope points, and they're collinear. Okay, so we have this intensity surface, this convolution operator, that derives from the definition of a derivative. And so let's say with this first convolution operator that we see, minus 1/2, 0, plus 1/2, that's going to give us our first edge point. We can put another convolution mass below it. That's going to give us a second edge point. When those two edge points we can use to define a line, namely the edge, be it a horizontal edge or vertical edge that you see in the image. Now, for good measure, we can make it a much more strong edge. Say, well, let's have more than 2 points. Let's have 3 points. And we can have an edge point below that to make sure it's not just an artifact of noise, that you have representation of 3 points. So we can absolutely use 3 points in our definition for an edge. Now, granted, 3 points does not define a line. 2 points defines a line. But we're after robustness here, not just necessarily the mathematical definition. Okay. So essentially, when we talk about an edge is nothing more than a steep hill in the intensity surface as defined by the gradient or the partial derivative along a scan line at three adjacent points. So here we have 3 adjacent points. There's the first point for position xy, the next position xy, the next position xy. We have steep hills at 3 adjacent points, and we're going to define that as an edge, right? One of these segments of this horizontal edge or this vertical edge or line. Okay, so we can actually measure 3 adjacent gradients with a single convolution kernel by taking these individual 3 vectors for a convolution kernel and replicating it associated with xy positions that are adjacent. And so this center point xy is adjacent to this other center point xy is adjacent to this center point. If we were to actually think about what these coordinates are in image coordinates, then I'll use red here. Well, if this is coordinate x comma y, this will be coordinate x comma y plus 1, and this will be this point, this pixel x comma y plus 2. So absolutely, the slope at this point, the next point, and the next point, those 3 points, they'll be adjacent. And if we have steep hills in the intensity surface at 3 adjacent points, as defined by the convolution operator, repeated 3 times, yes, absolutely, that is an edge. Okay, and so this gives you a precise gradient measure, and this particular convolution mass that we present by replicating the one-dimensional convolution mass 3 times along the x direction, we're not concerned about the actual gradient between the left point and the right point around the center of this mass. We're more concerned about the relative measurement between the center pixel and the surrounding pixels to the left and to the right, or the neighboring pixels around it. And so one of the things we can do is simplify this mask. We can simplify this mask, cleaning up this computation by multiplying it by 2. Well, if we're multiplying it by 2, all of these halves go away. The negative halves and the positive halves go away, and we're left with -1 and +1, and the 0 doesn't change. So we're going to clean this up because we only care about the relative difference, not the precise gradient measurement. Okay, and so this is a generic depiction of our convolution mass that's going to calculate these edges. And these give us the computation of the partial derivatives, both in terms of x along x image coordinate directions, x scan line, and the y scan line in the y direction in image coordinates. And so what we do here in this mask, it's 3 by 3, and we can think of it in 2 different ways based on the algebra that we perform with respect to the values associated with these weights and their position on the intensity surface. So in the middle of this 3 by 3 convolution mask, we have image coordinate ij, and then we have scalars going around, a0, a1, a2, A3, A4, A5, A6, A7, and then we have our center. Likewise, if we want to compute the gradient along the x direction, the x scan line, what do we compute? Okay, well, we look at the central difference between A2 and A0, okay? We look at A2 minus A0, okay? Because this will be positive 1, this will be negative 1. We look at A3 minus A7, we look at A4 minus A6. We group all that together, and what do we have? We have A2 minus A0, we have A3 minus A7, and then lastly, for that third scan line, we have A4 minus A6. Likewise, for the gradient along y direction, what are we going to do? Well, we just rotate this. We have the minus ones on the bottom, right, along here, and then we have the plus ones along the top. So we're going to say the central difference in the y direction, we're going to say A0 minus A6. We're going to say A1 minus A5. We're going to say A2 minus A4. We group all of them together. Here we have the gradient along the y scan line direction in image coordinates, A0 minus A6. We have A1 minus A5. We have lastly A2 minus A4. Now, for emphasis, we can multiply the central row or the central column. So here's the central row. Here's the central column. We can amplify the impact of that by multiplying that by a constant. We're going to call that constant C. So here, for the scan line in the x direction, we have C times A3 minus C times A7. So we have CA3 minus CA7. Likewise, for the scan line in the y direction, we have C times A1 minus C times A5 to amplify the center of this mask, the contribution to the slope. We have C times A1 minus C times A5. So this constant C places emphasis on the center of the convolution mask. And so with this, we can actually compute either the partial derivative in the x direction along the x scan line in image coordinates or along the y scan line in image coordinates. Okay, so we can compute these gradients along x and along y, and we can actually combine these gradients with respect to x and y, treat them as an x component and a y component, and calculate the magnitude of the gradient of the edge, as well as the angle or orientation of the edge. And so we use the Pythagorean theorem. We just take the gradient with respect to the x direction, we square that, add it to the gradient with respect to the y direction, we square that, we take the square root of that sum of those squares, and that gives us the gradient magnitude. For the direction, well, we just use inverse tangent, which is the gradient with respect to y over the gradient with respect to the x scan line. We take the inverse tan of that, and that gives us theta, the angle of the edge. So now with this approach, we can get the magnitude of the edges as well as the direction of the edges, in addition, above and beyond just the raw scan lines along x and y, those gradients. Okay, and so in the computer vision literature, you'll see two operators that are pretty famous for extracting edges. One's called the Pruitt operator. It takes this 3x3 two-dimensional convolution mask and it sets that constant C to equal 1. And then the Sobel operator, it's the same 3x3 convolution mask, only that constant C is set to 2. So here we have the scan with respect to x, central difference with respect to y. Here for Sobel, the first S of x is the central difference with respect to x, and we have the central difference with respect to y. Okay, so now we have these operators, the Sobel and the Pruitt. We can calculate our gradient. We can do the magnitude and the angle. Let's try this out in MATLAB. And so here we have our convolution mask, and the first mx is our mask, our Sobel, rather Pruitt operator with respect to x. So we have the first row of the matrix, second row of the convolution, 3x3, and third row. And then this is your mask for the scan line in the y direction. We're going to do a two-dimensional convolution we're going to take a black and white version of an image. We're going to do the two-dimensional convolution. So we take this mask and we slide it along the image and then change the row, slide it along the image, change the row, slide it along the image. And so Conv2D does this for you, and you just define that convolution mask for the SOVAL. And so then the result is our derivative with respect to x, and we get the derivative with respect to y. So now we're going to compute our edge map. We're going to take the magnitude of our edges. So here is the x gradient squared plus the y gradient squared. We're taking the square root of that. And then the angle is the inverse tan, the arctan, of the gradient with respect to y with a tensor division gradient with respect to x. So that's the y component over the x component. We take the arctan and we give our edge angles. So now what this quiver will take your gradient in x and y, and it will actually plot those vectors in 2 dimensions. So you can actually see little arrows representing your intensity surface. All right, so let's bring up MATLAB, and we'll take a look at how this works in practice. So here we have the same commands. We have the image, and we're going to call this image, I've called it a dog's life. So let me run that. Oops. So let me run that and read in the image, and let me pop up a figure, and I'm going to show that image. So this is the original color image in RGB color space. That dog is having a great time, nice and relaxed. So we're going to convert this image to grayscale. So let me step over that, pop up figure 2, and this is the grayscale version. Now, I could have easily extracted the red, green, or blue color channels and done this processing, but I've chosen to do this on the grayscale image instead. So I'm going to construct my 3x3 two-dimensional convolution mask for the x scan line and the y. So if we look at the x scan line convolution mask, we have +1, our central difference, and -1. We have -1 is 1, -1, 1. Right? So this is our convolution mask, and the y scan line convolution mask, you see we have the first row of this 3x3 matrix, all -1s, and then the third row is all +1s, just as we had discussed before. So I'm going to perform the two-dimensional convolution for x, and we'll step through that. And then I'm going to take my 2D convolution in x, and I'm going to say display those slopes, those gradients that are greater than 100. So let me step over that, and I'm just going to show those gradients that are greater than 100. So this represents a DDX. So as we go from left to right, you see some of the ways here. We also see most prominently the edge of the dog's jaw, and then we also see very prominently that crease in the middle of the dog's face. Here's that crease. That is a vertical edge, and it's picked up by running a scan line from left to right. We also see that edge of the seat for the boat, and we also see very prominently that part of the cloud where we go from light to dark, right? So these are all of the vertical edges, the strong vertical edges whose gradient in the image intensity surface along x changes by more than 100 intensity values. Okay, so let me do the same likewise in the y direction for the y scan line. And here we see all the horizontal edges. So you notice here, it's a different set of edges. If you look at the black and white image and you go down on a scan line, while you go the dog's head, you see that. You see the motorboat, you see this edge a little bit, but you very prominently see the ripples on the wave, right? They go as horizontal edges. You see the horizon here where the sea meets the land quite prominently. So those are all of the horizontal edges that are represented as gradients along the scan line in the y direction in image coordinates that are greater than 100, so the change in the intensity surface in the y direction along the y scan line is greater than 100. Okay, so now we're going to compute the magnitude. So we're going to take the square root of the x and the y components for the gradient, and we're going to compute the magnitudes, and then we're going to look at a histogram of the magnitudes to show you what these magnitudes are. They're kind of more centered, closer towards 0. And I have a little bit of a bug glitch that happened in MATLAB, but let me continue. And then I'm going to show the image magnitudes that are larger than 55. Okay, so I do that, and you notice here I get a nice little outline of my image here. But it's a little bit noisy because I'm taking all of the magnitudes, but I can certainly display this quiver, which is a pretty interesting plot. Let me do that. So let me type here quiver ddx ddy, and we'll bring that up and we'll see what we get. So this is the quiver plot, and let me rotate this. Let's see. Grab this, and let me try to rotate this. Let's see if I can rotate this. So let me do this, and let me grab this that's panning. So let's see if I can flip this. Rotate. Let me flip. Oops. Tools. Let's see. Align. Options. Restore view. Rotate 3D. Okay, so let me just see if I can rotate this. If it'll allow me. Nope, I don't want to rotate it that way. I rotate it that way. Okay, there we go. So it's left to right. So let me try to flip this so that it aligns with the image. So rotate along that axis. I rotate along that axis. There we go. Oh, okay. So let me rotate there. Okay. Oops. Rotate there. There we go. So there. Oops. There we go. So let me rotate like that. Okay. And here we are. So let me zoom in. Let me zoom in. Let me see if it'll let me zoom. No. So zoom. There we are. So if we zoom, and let me grab, slide this over, and let me zoom again. Oops, zoom this way. Zoom in. Oops, it's not letting me zoom. There we go. There we are. So zoom again. And we're just going to look at the side of the dog's face. And if we zoom in enough with this quiver plot, you will see, here we are, the edge gradients. And so here we see the individual gradients. So here's an edge. It has a higher magnitude. It's a vector. It's called a vector field. And there's this direction. So if we look at the edges associated with one side of the dog's face, you'll notice there are a lot of oriented edges that describe the shape, if you will, by looking at the gradient information and the orientation of those edges. So here we have the seam for the dog's nose, and you can see that they're aligned left to right going in that direction, right? Whereas along the side of the face, it's oriented in a different direction. And so the edge distribution in terms of the magnitudes and the orientation of the edges tells you a lot, let's zoom out, about the image content. And there is the quiver plot. And so here we have the image, we have the horizontal and vertical edges, and then we have the edge magnitudes. and we can take those edge magnitudes and quiver plot and get that information looking and actually visualize the vector field corresponding to the edge magnitudes and the edge directions. Okay, so let me exit MATLAB, and this is a demonstration of a representation of features that describes the image content. All right, so I'm going to end there. That's all I had for today. Again, please make sure that you're getting the reading done, and I look forward on next class meeting on Thursday to seeing your presentations. So as always, please stay healthy and stay safe, and I will see you Thursday.